Hey, it's Mr. Shrum, and we're picking up right where we left off on the magnetic forces tutorial. So we went over those two right-hand rules. The curl rule, where your fingers curl around the current carrying wire, and that will tell you the direction of the magnetic field. And then we have the palm rule, which will tell you the force exerted on a charge passing through a magnetic field. Okay, so let's practice those in this activity. If a charge travels through a magnetic field, it experiences a magnetic force, and its velocity is perpendicular to the direction of the magnetic field. Answer the following questions about the situations given below. Part A. What is the direction of the force on a positive charge when passing through a magnetic field as indicated in this diagram? Explain how you got your answer. So we have this positive charged particle moving to the right with this velocity. And the direction of the magnetic field, B, is pointing down. So with your right hand, point in the direction of, okay, so put your thumb in the V direction. You see how this Q, let me annotate. There we go. So your thumb, point your thumb in this direction. Okay. You point your thumb in the direction of the current or the charge. So put your thumb that way. And then we're going to use the palm rule. So put your fingers flat. Your thumb's going to move in the right direction. And then you're going to point your fingers down. So point your thumb that way, fingers down, and then your palm, whichever way your palm is facing, that's going to be the direction of the force. And if you do this correctly, your palm will be facing the screen, right? So the answer is into the page. Your thumb is along the velocity of the vector, and your fingers travel along the magnetic field vector to leave your palm moving into the page. Okay, let's try that again. Clear. All right, so part B. What is the direction of the magnetic field above and below the current carrying wire where the current is flowing in the positive X direction? Okay, so the arrow is pointing which way the current is moving. Now we're going to use the curl rule. Okay, let me get my annotation out. So that's where you point your thumb in the direction of the current that way. And then whichever way your fingers are curling is the direction of the magnetic field. So if you're pointing your thumb this way and then curling your right hand fingers, your fingers will curl around this wire, okay? And if it's below the wire, it's going into the screen. And then above the wire, it's coming out of the screen. Does that make sense? You have to think in a 3D mentality. So here, I'll color this in. Ooh. Actually, let's redo that one. So that one there. Maybe that makes more sense. Okay. So you see how it goes in behind the wire and then comes back out the top, and it's curling around the wire. So below, the magnetic field is going into the page, and then above the wire, it's coming out of the page. Cool. The direction of the magnetic field is out of the page above the wire and into the page below the wire. When you point your thumb in the positive X direction to represent the flow of current, the field curls out of the page above the wire, but curls into the page below the wire. Okay? Let me line it up again. Does that explanation make sense now? Okay. All right, so last one, part C. Why aren't the right-hand rules used to figure out the force exerted on particles traveling parallel to a magnetic field? Well, you can use the right-hand rule technically to understand that, but a magnetic field does not exert a force on particles traveling parallel to the magnetic field. Remember, it has to be perpendicular. That's the nature of these electromagnetic particles and current carrying wires. If it's going along, if it's parallel to the magnetic field, it does not experience a force. Electromagnets. An electromagnet is a type of temporary magnet. It's formed when an electric current travels through a coiled wire that is wrapped around a core magnet. The strength of an electromagnet depends on the type of core used. It's usually iron, the flow of electricity, and the number of loops in the wire. Scientists understand how to create electromagnets thanks to Ørsted's experiments, which found that electric currents can produce magnetic fields. The stronger the current, the stronger the magnetic field. Recall that a solenoid is a long piece of wire coiled to form many loops. When you apply the first right-hand rules to the loops, you find that the direction of the magnetic field in each loop is the same. Since the fields are in the same direction, adding loops increases the strength of the magnetic field. Since electromagnets require an electrical current, you can easily turn them on and off. This property gives them many uses in technology and the sciences. In the medical field, one of the most important uses is in the MRI. That stands for magnetic resonance imaging. An MRI scan provides detailed images of bones and connective tissues, organs, and blood vessels, or abnormalities like tumors. Doctors use MRI machines to diagnose diseases and injuries. Another use is in mass spectroscopy. Industries and crime detection agencies use mass spectroscopy to analyze and classify substances. Here's a brief explanation of how that works. Particles are ionized. Ionized means they're charged, accelerated into motion, then deflected by a magnetic field. And that process determines the molar mass of the molecular components of unknown compounds, which then leads to their identification. So they charge these particles, they speed them up, and then they introduce a magnetic field, and that deflects them. And then from that information, they can determine what type of compound it is. Many products work using electromagnets. Stereo speakers, doorbells, magnetic locks, audio equipment uses electromagnets to both record and reproduce sound as an alternating electric current. Here's an example. The electrical signal for the musical note A4 is an alternating current with a frequency equal to the sound frequency, 440 hertz. This alternating current changes the polarity of an electromagnet in your speakers 880 times a second. First, sending in one way, then the other, 440 times a second. You can use a right-hand rule here too. A speaker cone, which has a permanent magnet and an electromagnet interacting with each other. So one is always a magnet, and one becomes a magnet when electricity is running through it. Interacting with each other goes in 440 times and out 440 times in a single second. So that means it creates 440 complete compression cycles of the air in front of it every second. The emitted sound waves is a pure A4 at an audio frequency of 440 hertz. So electromagnets are really useful, and they're still being researched, and scientists are finding new ways to utilize them. Remember, the strength of an electromagnet is determined by factors like the flow of electricity and the number of loops in the coiled wire. So here we're going to look at this simulation. Hide that first. Let it load. And then we're going to slide the battery voltage to 10 volts. Set the number of loops to 4. Select show field meter. Here we go. Show field meter. Loops 4. Well, 10 volts. Okay. Place the meter along the axis of the coil and at the center on the tiny compass needle, 5 needles to the left of the coil. Be sure to take all of your values along the axis of the coil. You'll know you're on the axis because the Y component of the magnetic field is 0 along the axis. Record the values of B in the table below, and then repeat it on the right side of the coil, recording values for positions +1 through +5. Okay. Okay, so basically, put this over here. You're going to count over the needles 1, 2, 3, 4, 5. And until this Y component is about 0. So this is close. And then you'll write down the B. Okay. Here. So at -5, treat each of these needles as you would on a graph paper. This is -5. Write down that B, and then you go to -4. Write down that B, but make sure this Y component is always 0, You want to stay on this level through the coil. So -4, -3, -2, -1, +1, +2, +3, +4, and then +5. Okay, so pretend this is a graphing paper, and that's the center of the graph. And you're just taking this 5 points on the left and then writing down that B in these points. Here's the simulation. And it's really sensitive, so if your numbers aren't exactly like this, that's fine. But this is what you should get, usually. So what happens to the value of the magnetic field strength inside the coil? Well, it's the greatest inside the coil. Look, so outside the coil, it's not very strong. And then all of a sudden inside the coil, it's 300. So that's a lot more. And then you can go back. Let's just put it inside, okay? So well, if you reduce the number of loops, the magnetic field strength decreases. If you increase the number of loops, the strength of the magnetic field increases. So the loops add strength to the magnetic field. Checkpoint question. What is the final step when using a right-hand rule to determine the direction of the force on a wire in a magnetic field? So that's the palm rule, okay? Thumb points in the direction of the current, fingers point in the direction of the magnetic field, and your palm pushes into the direction of the force. In which case will an electric charge experience a magnetic force? Remember, an electric charge, a negative electric charge, is traveling perpendicular to a constant magnetic field. And I'll stop here for now, and later we'll talk about the problems with magnetic forces. But until then, have a great rest of your day, and I will see you all later.